Please welcome Mr. Pete Klupar, who will give us an overview of the STARSHOT system, as well as, in fact, the entire Breakthrough Initiative. Pete?
Thanks, Jim. Thanks for all you guys coming, and thanks, Les, for setting this up. I think it's really important that we do pull together, and we do have we stop the fractionization of the groups, and that we all kind of pull them together. STARSHOT will try and do our bit to focus, so we have a focused, applied effort for the entire journey to the stars, because it's going to take all of us to get there, because it is a really, really hard problem. Dr. Warden sends his apologies. He did get called away to Luxembourg at the last minute. He was planning to be here, but he couldn't make it. So I'd like to start with a video. We paid a lot of money for this video, so you should like it, I hope.
We are here. This is home. But for most of our history, we knew only our cradle in the corner. We awakened on this tiny world beneath the blanket of stars, without a note to explain where we come from, who we are. We inhabited a tiny universe, oblivious to the rest of the cosmos. It was only 4 centuries ago that we began to use science to reveal nature's secrets and her laws. What is science? It's an epic journey of discovery. It's a continuity of minds. It's standing on the shoulders of the giants who came before us, looking out across a valley, over a hill, up to the sky, and asking, I wonder what's there.
Oh, that view is tremendous.
It allowed us to look across space and time, see the scale of the universe, and our place in it. We now know that our galaxy alone holds hundreds of billions of stars, and that the visible universe contains at least 100 billion galaxies. In the last decade, we have discovered over 2,000 planets beyond our solar system. It's now estimated that there are tens of billions of habitable planets in our galaxy alone. Are we content to gaze at all these stars, all these worlds, from afar? We have taken to the sky. We have stepped off the Earth. We have walked on the moon. We have landed on planets and comets, and ventured to the edge of deep space. Where now?
It is quite an impressive video. I do like it, and we are very close. It occurs to me, looking around the room, that we do have a lot of STARSHOT leadership here. Of course, you've already met Jim. There's also Phil Lubin in the back, Phil, and Bob Fugate in the front row, and Kevin Parkin also. These are principals, all principals in our effort, in our STARSHOT effort. So over the next few days while you're here, if you have questions, please ask them. They're the smart guys. They know all the right answers. The slides, please. Also, if our email addresses are down there at the bottom, Warden's is, this is Warden's, and this is mine. I recommend, please, I also have cards. If you hit me up for a card, I'll give you one. It has address on there too. Please, we want to have interchange with folks. We want to talk to people and find out where the good ideas are, and make sure we can include them in everything. And I guess these slides will be in the presentation. Yeah, in the proceedings. Yeah, so they'll be there. So I'll quickly go through these slides. The Breakthrough Foundation has got two groups. One group is the prize. The prize is $3 million given to, in 7 categories, about 12 people a year receive it, and it's funded by the group of people here at the top. They're very wealthy individuals in Silicon Valley. The intellectual leader of this is really Yuri Milner. He's the one that gives us the inspiration. The prize is given out at Ames in November timeframe, and it's trying to make science popular. It's trying to popularize technology in the world. And there's another prize that people don't really hear about, and I would like to solicit your guys' help in trying to spread the word about it. It's called the Junior Prize. It's a scholarship given to students from all over the world. What they have to do is they have to make a 5-minute video on some science or technology item, and what's awarded is a $250,000 prize as a scholarship to the students, and then $100,000 given to the school for a lab, and $50,000 given to the teacher. This prize, it just closed last week, so you missed it last week, but if you know anybody who's 16 to 20 years old, please tell them about this. They might be interested. They might be able to win it. Here's, we actually awarded 2. We couldn't decide on which one to pick. So last year, these are the 2 ladies that won, one from Peru and one from Singapore. They're very interesting to watch the videos online. That's just at Breakthrough Junior Prize. So I would encourage it. So the question is philanthropy in space. Why should, for the last 50 years, all the space has been dominated by large companies or large countries, which is true. But if you go back 100 years, you'll find that most of the space stuff, for instance, Goddard here, was supported by philanthropic folks. And what we seem to forget is that when they went to the North Pole, when they went to the South Pole, those were all funded by what you might call Kickstarters, what we would call today Kickstarter-type campaigns, plus some large foundations. So there is a rich history of folks finding money in rather unusual places. And Breakthrough Initiatives is our effort to do that. Again, this is a picture of Yuri Milner. And the basic question that we're trying to answer is, where is everybody? It's the Fermi's paradox. There's all kinds of answers, many of them very interesting. And we've divided the work in the Breakthrough Foundation into 5 different tracks, and I'll talk briefly about a few of them. The first track that we started was Listen, which we started 2 years ago. And we're partnering with Berkeley and CSRO and the SETI organization, SETI at Home. And what we do is we rent 4 hours a day on the Green Bank telescope, 4 hours a day on the Parkes telescope, Green Bank is in West Virginia, Parks is in Australia. That gives us coverage on both. And then we also rent about 6 hours a night on the Automatic Planet Finder telescope in California. We have some arrangements with the FAST telescope, the 500-meter telescope in China, and we're starting discussions with some friends in a wide field telescope in Ireland. Our goal is to look at 1 million stars, the galactic center, and the 100 nearest galaxies, and try and I don't want to say, well, try and professionalize, try and define what we see and what we don't see. There have been a lot of searches out there, but they haven't really established what the threshold of where there are no signals coming from and would like to do that. Currently, we're collecting 2 petabytes of data a day, and we're washing through there and looking for signals, and basically 1 day of listen is equal to a year of all the previous searches. Like I said, there's been 5 previous searches, and this is most of them have only been down in the 1 to 4 gigahertz range, and they haven't actually measured much of the sky. So Jill Tarter's idea about taking a glass full of water out of the sea and not seeing any fish doesn't mean there aren't any fish in the sea. We also have an effort to talk about, this is a message that was sent from Arecibo by Frank Drake and in the 70s, and we have a group that's looking at, well, okay, if we hear a message, what message do we send back? Should we send back a message? Okay, I'll briefly also talk about WATCH. WATCH is looking for stars within 5 parsecs of the Earth, and our current target is Proxima Centauri or Alpha Centauri A and B. Here's a graphical representation. The thing that always amazes me about this picture here is, what are the chances that the closest stars to the sun are one that's slightly larger and one that's slightly smaller than our current sun, considering that 60 to 80% of the stars in this local area of the galaxy are red dwarfs. It's actually quite amazing. Here's a picture of the closest 5 parsecs. The colors are the temperatures of the stars, and you can see this is range north and south, and you can see and the circle size, the size of the circle shows the size of the planet would be if it was in the habitable zone around those stars. And you can see that Alpha Cen is a unique target that's close by and is large. So we're really lucky that we have Alpha Centauri A and B, actually. So we're in Breakthrough Watch. We're funding an instrument on the VLT. We're working with instruments on Gemini and Magellan, and we're also doing a study, an astrometry study for a space-based telescope to actually make an image of it. And here's some these are computer models of what it might look like if we actually find a planet. So we're limited to, we've limited our search to 5 parsecs, 15 light years, because we feel that if you're going to have a conversation with somebody, if it's 15 years one way, 30 years round trip, that's probably close to the limit of what you'd be able to sustain. Anything longer than that is probably undoable. So we consider this our target area. There are only 10 sun-like stars, 46 red dwarfs. We're not really sure how many brown dwarfs. But that's really our target list. It's not many, So they've already found a habitable planet around Proxima Centauri, and this is the guy that did it, Gillum, out of ESO. He went and he looked through. He didn't actually do a new campaign. He went and he looked through data that was already there. And by the way, that's Pete Worden. So if you see him in the airport, you can yell at him. And this is Tim Dezoe. He's the head of ESO. Artist concept of what it might look like on Proxima A. Another thing we're doing in Watch is Enceladus, because we're looking for life in the universe, and the solar system is part of the universe. And we looked at all the different water worlds that are in our solar system. And we considered all these are the craft that have all gone past Jupiter. There's not really a whole lot of them. But Enceladus is an interesting place. It has these large geysers that are 150 kilometers tall. And they seem to be spewing out hydrogen-rich, salty water, which is really quite unusual and suggests that there might be some kind of thermal vents, volcanic vents down at the bottom, caused by the moon orbiting Saturn. And there might be enough energy there for life to exist. So we're studying whether or not we can go and take a sample. There are four tiger stripes with each one of these circles is a vent. And this red line is how Cassini went past it and what they explored. The idea we had was get on a big rocket and put 10 very small CubeSat-like objects on it and fly by. Here's some payloads. The different types of payloads are mass spectrometers, the UV cameras, Viz cameras, spectrometers, and chemical analyzers. The problem is the plume comes and it goes, and so you've got to hit it during where these red circles are. So it's about every 3 years there's an opportunity to have the richest. Here's just a representation of the planet, or the moon. It's a very interesting place. But now what we really want to talk about, which is STARSHOT, which is something that you'll hear quite a bit about. And the question is there a Moore's law for speed? If you chart it from about 1850 on, up till about 1980, it seems to follow the curve. But then somebody didn't make an invention they were supposed to make. And I don't know which propulsion guy it was, but Huntsville is noted for propulsion, right? So maybe it's somebody around here. So we need to have a Helios 2, up until the Juno mission, Helios 2 was the fastest object, and it was 1976. It was 70 kilometers a second. And so how long is it going to take us to get past that barrier that we've seen? The rocket equation is really hard. It really says that your ISP is what drives you. And in order to get to percentages of light speed, we really need to, would like to get close to 1 million ISP, which right now we're at about 200. So this guy is 200 to 300. That's a long way from 1 million. Even the atomic rockets, the nuclear and the fission guys don't quite make it. Antimatter comes close, but it turns out we need 1,000 years production of antimatter to get us to the nearest star. So 1,000 years of antimatter, of the human production of antimatter, is probably out of the reach. There are some, I'll call them far-reaching approaches. fusion. These guys have come up with a concept of fusion that might work, but if these guys actually crack that nut, we're going to have Mr. Fusions in the back of all our cars, so we're not going to have to worry about energy again. So that'd be positive, but it's a bit far-reaching. Then you also have people like Sonny White working on things that we really don't understand yet, and so it's difficult to understand how to apply things we don't really understand. So that really leaves us with one thing with sailing on photons. It was first proposed by Kepler back in 1610 in his letter to Galileo. And so it has a long history of working, and we also have some very recent examples of people sailing on solar winds. Here's a brief roadmap of where we're planning on going, and I guess what we basically say is right now we're doing basic development, and then we're going to go into the research phase in about 5 years, and then into the production phase, and to get to 20% the speed of light. But you can see even our time horizons are with launches out in the 2040s. We have a lot of challenges, and we've listed them, and they're on our website. And we've been working on the challenges, and what we're focused on right now are the sail and the laser, and also communications. So those are our 3 thrusts for the next 5 years. We're about to release an RFP to go on the laser area, trying to combine an infinite number of lasers into one machine, and in about sometime in the late winter of this year, we're going to release the sail RFP, and then the communication RFP is going to come out in the spring, summer. Could we play the other video? So the RFP that's coming out on Friday is for combining the infinite number of lasers. We're really looking for ideas about people who can coherently combine 2 trillion lasers. It's a small number. Yeah, a piece of cake. So this is an artist rendition of the array. This is what we call the mothership, and then there's the sail. We have this targeted in the place in the Atacama Desert in Chile. This is supposed to be at least 1 kilometer by 1 kilometer. Some people think it should be 5 kilometers across, so it's a pretty big thing. It only shoots for 2 minutes because there are a lot of spacecraft in orbit that it could hit, and this is a pretty bright beam, so it could damage them. So it hits the sail for 2 minutes, and then it flies for 20 years. And it goes edge on so that it has minimum exposure to the dust in the interstellar media. And the artist even put a little bit of speed of light sort of drag there, and then somehow it magically slows down by the artist. The artist had it slow down here. I don't know how that happens, but we basically have 10 seconds to take pictures. So we travel for 20 years. We have 10 seconds to take pictures to be within 1 AU close to 1 AU of the planet. And then we use lasers and send back the comms back with a large laser pulse to the Earth, and use the same array as a receive array to get the message. Maybe you could play that one more time, just because it does go there pretty quick. So again, these are supposed to be lasers, but I don't know. It worked okay. but again, there's the lasers, and we think that the field of regard of the lasers are probably going to be in degrees, not like it was shown there. Another big problem, it's 100 gigawatts of power developed, 30 to 50 gigawatts on the sail itself, depending on what assumptions you make. So doing that out in the middle of the desert in Chile is also quite a challenge. And it was a good point about what Les made when he kicked this off. If we're going to launch in 2043, we get the signal back in 2067. What can we do now? I mean, 20 years ago, I was taking pictures with a Kodachrome, right? Then I moved to video cameras. I can't even find a VHS around, let alone a beta. How am I? And then we went to DVRs. How are we even going to draw a straight line with keeping the data together, let alone having it be relevant to folks? So I think that's it's a very big question that that's hard to answer, and also I would also argue that we live in a Facebook world, and in the Facebook world there are people that can spend an afternoon, Sunday afternoon, on this problem, and if we could present them a problem that they could work on, some kid in Mumbai or Beijing or someplace, if we could set it up so that they could electronically contribute, I think that's going to help us solve these problems. But I think that's a huge, for an old guy like me trying to figure out Facebook, I don't know, let alone coming up with an engineering solution or an engineering way to have that interchange. We're working on it, but we'll see. There we go. So we certainly can't send a big spacecraft like this on a journey like we just showed. 7,000 kilos is not going to work. We have to come up with these little guys, This kind of gives you an idea of how little they are. It's 200 milligrams, and it has a laser. It has much of the functionality that we need: laser, processor, memory, photon engines for steering. And we were able to launch 6 of these on this year on a PSLV, and 3 of them got trapped inside a non-functioning spacecraft, but 3 of them were released, and we talked to them until they deorbited. They were in a very low orbit, so they didn't stay up well. But this basically has the same functionality. This thing here has the same functionality as this 200 milligrams has the same functionality as a Sputnik. So we've come a long way. Okay, so if you have the chip and you have the sail, we call that the star chip plus the sail. We call the nanocraft. So our initial, we talked about this, the laser device development, RFP released on Friday, sail development RFP released in February, and laser communication sometime in the summer. We're also looking at, so we're thinking about experiments we can do in the near term. What are the things that we can do now to keep the people excited and keep people interested? And so one of those things we thought about is if we were able to develop, it seems like the materials are being developed quicker than the laser technology. And we may be in a position in 10 years to have a sail material with the correct aerial density to be able to visit some of the planets in our solar system. So some of the things we've been thinking about is if you dive down to very close to the sun, much closer than Mercury, you can get accelerations, and you can go out. You can make it to Jupiter in months, to Pluto in less than a year. So it's an incredible thing that you might be able to investigate all of the solar system for very low cost. Here's some of the times. And the other part that we also think about this, that I'm always worried about, is we understand really well out to Pluto, but what's going on in the interstellar media is less than obvious to us, and yet we need to build a vehicle that's going to be able to survive that trip. So we need a lot of work in that area. I have a few minutes for some questions. I'd like to see if anybody's paying attention. Or
I noticed in the study projects we're pointing the parabolic dish antenna out in different directions, and some suggestion has been made that the signal might be there by a broadband kind of transmission, or it might the signal might come from multiple directions at once. We have the means to find it.
so the question is, could we have a broadband approach to SETI to look across the whole sky? Andrew Simeon will be here and talk tomorrow, I think, and you should really ask him. But we are doing studies into how to actually do that with some of the new telescopes that the square kilometer array that's coming online down in South Africa. So yes, we are trying to figure out how to get these wideband signals. We are looking at it. Just talk about, I'll repeat your
The
question.
sun grazer is a fascinating concept. It doesn't really seem necessary to wait 20 years or 10 years to start testing that concept. So how ambitious should we be?
Well, right now we can make square centimeter size material for that has the aerial densities that we need. We need something that's square meters. So how fast we can expand that material is really a question, and that's what we hope to answer with the RFPs for the sale.
But the concept is good to use to do a sun grazer slower approach, not with the laser powered approach. I think
Right.
we use sunlight pressure to get a lot of
Right.
acceleration.
Yes. We can get you can explore the interstellar media with the solar pressure, but probably not go to interstellar distances in reasonable times. I mean, you could if you just waited. Or what is it? Mote in God's eye. Yeah.
How and where will the RFPs come out? How will we find those?
Come and see me. We're a private foundation. So how do we get the RFP? We're a private foundation, so we don't have Business Daily or any of the normal distribution channels. Frankly, we'd like to get as much participation as we can, and come and see me or come and see Bob. Bob will love that. Yes, we post them on our website. But I think it's better to talk. Since we don't have the FAR, since we're not a government thing, it's much better for us to have discussions and to make sure you're on the right track and don't waste your time. But it's only 4 pages, so but it's also only 150K. So we're starting slow to build to a reasonable effort.
Down there?
It's about the budget pie chart, not how much it will cost.
Okay, so where's the pie chart for funding? We think that this effort is going to cost on the order of a CERN of $10 billion for the total effort. And we think that 60 to 80% is in the photon, what we call the photon engine. And that's divided between the telescopes and the lasers and the combiners. So most of the money is in the photon engine, and then and Bob will talk about that. And then the rest of it is the mothership and other things.
A couple of years back, there was a group called Escape Dynamics that was doing some really promising research into microwave propulsion. Has anybody looked into that? I know that they ended up having to shut down because they didn't have funding, but I know that they actually did a small scale, and it looked very promising. But then, I don't know if NASA picked it up afterwards or whatever, but I just know that they ended up shutting down, not because it wasn't promising, but just they couldn't have that funding.
I'm really not familiar with escape dynamics. We've studied microwave a little bit. The problem with microwave for interstellar work is that you need a gigantic ground. If you commit to ground-based, you need a gigantic ground-based array, and we thought that was too expensive. Now we've been talking about doing near-term tests in the microwave to understand stability and to possibly move around the solar system, but we're still studying that. So it's a good idea, but we're still looking at it.
Anyone else? Yes?
Yeah.
Are we looking at the possibility that there are natural processes which seem to exhibit the process of excess speed that may give an insight into improved propulsion technologies? And in particular, I'm thinking about comets. The conventional explanation for comets is that they're somehow bumped out of the Oort cloud every now and then, and they come into the inner solar system. Problem with that explanation is that some groups, such as the Kreutz and Marsden groups, the sun grazers, are very frequent and directional, and also very fast, 60,000, 70,000 miles per hour. You follow the question?
What's the question?
The question is, are we looking at it? Is anybody considering the possibility we have a bad explanation for an interesting process that could give us insight into better propulsion technologies?
No, I don't know of anybody working on that.
Okay.
And I would also say that the speed that comets go are very fast, but we're talking about 3 or 4 orders of magnitude faster than those guys. So it's a significant, it's a start, yeah.
Shall we move on then? Thank you.